to take our first look at finding the area of an irregularly shaped region. We're going to do that by using a function. This is commonly called finding the area under a curve because it is typically talking about the region bound by the curve and the x-axis. So this whole space in here. Now, that would be roughly triangular in shape. Not perfect, but I suppose you could argue that a triangle would give the best estimate. Now that being said, it would, but that's unique to this particular region. There are other different regions where a triangle might not be appropriate, where a different shape might give a better estimate. So the idea here is not to pick a shape, a geometric shape that gives a good estimate for this particular shape, but to try and come up with a generalized process. Now, whatever geometric shape we end up using, we are finding area, so we're going to have to calculate area. And of all of the shapes out there, there is nothing easier to calculate the area for than a rectangle. It's got the simplest calculation, just height times width, or length times width, or base times height, whatever phrases you want to use, but it's literally just how wide and how tall is the triangle, or is the rectangle. Even a triangle has a 1/2 times base times height. There are many other shapes out there that have more complicated area formulas. But our goal is to try and keep this as simplistic as possible in whatever ways we can. So I'm going to suggest that we use rectangles. Now, there are different ways to set this up. Because, first of all, it depends on how many rectangles we're using. Let's start with the idea of a single rectangle to kind of represent the whole region of this. Now, I suppose what we could do is have a rectangle whose base lies along the interval of the x-axis. I mean, that would seem to be reasonable, whether we're using a triangle or a rectangle or some other shape. That would seem to be pretty reasonable because that is one of the borders of the region. Now, that being said, we now would need to have to figure out the height of the rectangle, and there are 3 schools of thought for this that are commonly used. We're going to let the output value of the function, the y-coordinate of the function, determine how tall the rectangle is going to be. And there's really 3 decent options here. We can base the height of the rectangle off of how high the function is on the left side, which in this case would mean 0 height. Obviously a terrible estimate, but again, that has to do with the shape of the graph on this particular interval. We could use the midpoint, that is to say we could go to the center of the interval and we could use the height, the y-coordinate there, to determine the height of the rectangle. Now that seems a little bit better. Of course, it's not perfect. It is leaving off a whole section up here that should be included, but it's also including an extra section over here that really shouldn't be included. So it kind of strikes a decent balance. However, that's still not the one we're going to use because it does actually involve the most calculation. And much like the choice of a rectangle as opposed to a triangle is meant to ease our calculations, we don't want to go using something that's going to be more complicated, even if it does seem like it's going to be more accurate at first. The one we're actually going to use is the height at the right endpoint of the interval. If we base a rectangle off of that height, now, first of all, that is grossly overestimating the height or the area of the region. It does certainly include the entirety of the region, but it also includes extra space. Lots of extra space. So it's really not the best estimate at this time either. But as we've seen in calculus, if you recall from when we learned about derivatives, it's not about getting the best estimate straight out of the gate. It's about coming up with a reasonable way to make an estimation, and then later on we'll worry about making that estimation better. So, the idea is that we're going to construct rectangles whose base sits along the x-axis and whose height is determined by the y value of the function at the right side of the interval. So, in this particular case, the base of this is the total width of the interval, and that is 2. And the height, coming from the y-coordinate at the right endpoint of the interval, the height of the rectangle then is 4. So this rectangle here has an area of 8. That is the entirety of this whole region, which is definitely way more area than we want to have. Way more. If anything, because of the way this kind of bows out, because of its concavity, the total area of the region we want should be less than half of 8. So this is definitely a horrible estimate. Now that being said, it doesn't matter how good the estimate is at this point. It's just meant to help us establish a calculation, to help establish a way of getting the estimate. Then we'll worry about making it better. So, what we've got here is that we're going to estimate the area of an irregularly shaped region using the most regularly shaped geometric figure we've got, a rectangle. Now, how do we make the estimate better? Well, part of the problem is we're trying to estimate this whole thing with a single rectangle when it's definitely not rectangular in nature. So, what if we try subdividing the region? What if we treat this as 2 separate intervals that just happen to be attached to each other? Each one, we can follow the same guidelines for building a rectangle on. Its base will sit along the x-axis, and its height will be based on the y-coordinate at the right edge of the interval. We do that for the first section, and then we do it again for the second section. This rectangle, its base will sit along the x-axis, and its height will be determined by the y-coordinate at the right endpoint of this subinterval. Now, we can already see how this is going to be an improvement because the first rectangle included everything up here. We're now cutting away a section of that. So while we are still including some extra space, it's not nearly as much extra space as it was before. Of course, the trade-off is that we now have 2 areas to calculate, and we have to add them together. So we have increased the amount of calculation we have to do, but we'll get a better estimate for it. So, we now have the area of the first rectangle, which has a width now of 1. and a height of 1. So this first rectangle here now has an area of 1. But we have a second rectangle which we also need to find the area of. Now, its width is again 1. Now, there's no saying that we have to split the interval precisely in half, but why would you split it in a different way? I mean, that would seem to be the most natural kind of way to divide it, but it has the added benefit of keeping both rectangles having the same size base, the same width. Now, the height, of course, will be different because the y-coordinate at the right endpoint of this interval is different. So here we have 4 as our height. Now, if we add them together, we get the total area of the region being estimated at 5, which is, again, considerably better than what it had been. The first estimate with a single rectangle for the whole thing was 8, but we had a ton of extra space up there. Now we have much less extra space because this part is no longer included. We've kind of narrowed it down to just these two. Okay. Better. But not perfect because, again, we do still have a lot of extra space. We have everything we're supposed to have, but we've got too much. Well, if doubling the number of rectangles got us a better estimate, why not double it again? Instead of splitting this interval down here into 2 pieces, what if we split it into 4 pieces? Now, that's going to affect what happens with the heights of our rectangles because, well, we now have different bases. We have more subintervals to work with. So our first subinterval goes from here to here. The height is going to be the y-coordinate at the right endpoint of that subinterval. Then we have this subinterval. Its height is going to come from the y-coordinate at the right endpoint of that subinterval. Our third subinterval, the height is going to come from the y-coordinate at the right endpoint, and so on. So, again, we're getting an improvement because the previous situation went across there. We're now removing this section. And here as well. So while we are still overestimating the area, we're reducing the amount of overestimation. Now, once again, the trade-off for this is that while we will get improved accuracy, we're going to have, once again, twice the amount of calculation. We now have 4 rectangles to calculate the area of, and then to add together. But to make matters worse, the width of each of these has gotten uglier. In fact, the height has therefore gotten uglier. When it was just the one big rectangle or even the 2 rectangles, their heights were easy to determine. But this rectangle, its height is not so obvious. Same with this, not nearly so obvious. So what we need to do is realize that there's a way to calculate the height of the rectangle. We use the y-coordinate of the curve. And I'm going to say this, that the height of the ith rectangle is the output value of the function at the right endpoint of that subinterval. Now, we'll match the subscripts for now, so that the height of the first rectangle would be f of x sub 1, the right endpoint of the first subinterval. The height of the second rectangle would be f of x sub 2, which is the height of the y-coordinate at the right endpoint of the second subinterval. So you can see how this is going to get a little bit ugly. So the area of the first rectangle is going to be the height of the first rectangle times its width, where the height is going to be f of 0.5 times the width, which is 0.5. Well, now we have to calculate that, so it seems that we've more than doubled it because we now have to do a calculation to actually get the height of the rectangles. Now remember, the function here is f of x equals x squared. So fortunately, it's a simple calculation. To get f of 0.5, it's just a matter of squaring 0.5. Of course, this provides us with some values that are not the best, not very nice to use. Well, what you gonna do? Now, we have to repeat this for the second, the third, and the fourth rectangles. So the height of the second rectangle is going to be the output value of the function at the right endpoint of the second subinterval. So f of 1. Now, the width is again 0.5. You may have noticed actually that the widths don't have subscripts on them. I don't have w sub 1 or w sub 2. I don't need subscripts on them. I do for the heights, because the heights are different for each rectangle. I do for the areas, because the areas are different for each rectangle. But the widths are the same. And that's the advantage of always using equally sized subintervals. One advantage. We'll see another as we progress with this. So, 1 squared is 1. Unfortunately, this one's nice and easy. Now, we would have to do the same thing for the third rectangle. And for the fourth rectangle. But we are rapidly running out of board space here. So I'm going to take the liberty of not writing out all the steps, but just calculating these. 1.5 squared is 2.25. And then half of that is 1.125. 2 squared is 4. And half of that is 2. So if we want our estimated area, we need to add up these four values. 0.125 plus 0.5 plus 1.125 plus 2. Those are the areas of our four rectangles. Again, it's not pretty. Calculator comes in handy here. 3.75. Now, this process begins to get very arduous, very complicated, very involved, because every time we double the number of rectangles, we more than double our calculations. We have twice as many rectangles to calculate, but that means also we have twice as many things to add, and to make it worse, we have to calculate the width, because eventually, when we subdivide these, get smaller and smaller, that starts to get into some very ugly numbers. We also now have to, we can no longer visually determine the height of each rectangle, we have to actually calculate those. And then, again, the numbers for the endpoints of our intervals are going to get considerably more ugly as we go along. So there's got to be a better way to do this. Well, hopefully, having gone through the previous lesson on summation, you may have noticed that we are adding together a series of things that are subscripted beginning at 1. Summation is going to be the key to this. Of course, we do need to establish some patterns in how this is done first. So let's table this discussion at the moment. We will come back to this, but we need to find a better way to do it first.